That's really fun. Swag. If it was swag, it'd be us. Yes. Yeah.
Okay, are we all ready?
No.
The correct answer is yes, Mrs. Duran. We are ready.
Yes,
We are
Mrs.
so
Duran.
ready
We're
for
always
math.
ready. I would marry if I could.
Matt got married. I divorced her on.
I wouldn't show up to the wedding.
Run away.
You feel bad for no, like a bad joke.
I just realized you didn't happen to send out those emails, did you?
No, I have not sent anything out yet. It's been a very rough week. But they will go out by Monday. HA2 stuff.
Huh?
What if I said yes, Kendra, and you didn't get one?
That would be
Honestly,
it would be so well deserved. She doesn't even do homework.
I do.
She finished the homework we had 2 days to do. A few weeks ago.
No, I haven't sent them out yet. Okay, are we ready for inverse functions?
No.
Sure.
Correct answer is yes, Mrs. Duran, we are.
I'm gonna be honest.
Hey, I don't remember our interview for grades.
Newsflash, they are, and that's why half of us are failing.
I'm not feeling actually shunned Miranda. No, she shunned.
Wow. I'm feeling the love right now.
I did the one time.
You know how to give love.
I don't like any of this inverse stuff.
I don't
Oh, I love it.
What is the definition for numbers? I'm so ready. They feel entitled.
Okay, so we're starting off with inverse relations. So this is the set of ordered pairs obtained by exchanging the coordinates. So x's become y's and y's become x's. Of course, I will show you an example of what this looks like. So here's an example of a relation and then the inverse of that same relation. So my first relation is the set of ordered pairs 1, 5, 2, 6, and 3, 7, where 1, 2, and 3 are my x values or my domain values, and 5, 6, and 7 are my y values or my range values. The inverse then just took all of my x's and my y's and switched them. So my inverse relation is a set of ordered pairs 5, 1, 6, 2, and 7, 3. So 5, 6, and 7 are my x values or my domain values. And 1, 2, and 3 are my y values or my range values. So the domain of my original became the range of my inverse. The range of my original became the domain of my inverse. And this is just writing out that domain and range flip. So this was just formally writing out that the domain of a relation becomes the range of the inverse. The range of the relation becomes the domain of the inverse. So domain and range literally just switch spots when we start taking an inverse of a relation or a function. Does everybody see how my x's and my y's just flipped from my original relation to my inverse relation? Okay. Give you guys a second to finish writing. I can push it up if you need me to, Allison. I know it's hard to see toward the back. It's such a big class. Not the faintest idea. There's also another really cool relationship between a relation and its inverse, and we're going to find that out by graphing our original relation and our inverse relation. So now what we're going to do is we're going to graph these. Using that set of points as vertices, so each of these is going to be a triangle in the end, just so you're aware of what kind of we're going for. So first thing I'm going to do, of course, is draw my coordinate plane. This will be free-handed for each of us, so it's not going to turn out to be perfect, but that's okay. We have much not even close.
Oh, we have to do a bunch of graphics.
On today's homework? No, there's only one graphing problem on today's homework.
Did you put 6?
I did. So for this specific problem, we are going to use the original relation. One, negative 2, 2, 5, and 4, negative 1. And that means that my inverse relation will be negative 2, 1, 5, 2, and negative 1, 4. For ease, I'm going to go ahead and label each of these points as a vertice. So we'll just go in alphabetical order. So 1, negative 2 will be point A, 2, 5 will be point B, and 4, negative 1 will be point C. I would like to similarly mark my inverse vertices. So negative 2, 1 is going to be A with an apostrophe. We call that A prime. 5, 2 is going to be B prime, so B with an apostrophe. And negative 1, 4 is going to be C prime, or C with an apostrophe. For anybody who can't see that. Just so we keep them kind of similar so we can see the comparison. I'm going to color code this so my original points will all be in red, and then my inverse points will all be in blue. So we're going to start with point A. That is at 1, negative 2, so I'm going to plot that point. I'm going to put an A so I know. Point B is at 2, 5. And point C is at 4, negative 1. As best as we can, we're going to go ahead and connect these points. And then we're going to do the same thing with our inverse points. Again, I'm going to color code, so I'm going to use blue for those. So negative 2, 1 is my A prime point. 5, 2 is my B prime point. And then negative 1, 4 is my C prime point. We're going to go ahead and connect those. And then we're just going to look at it for a second. It doesn't have to be perfect. We're freehanding these, so I'm not worried about it being 100% awesome. Does anybody notice anything about these two graphs? Okay. So I like the way Brandon said it. He said there it looks like the inverse is kind of the original rotated. So I'm actually going to go one step farther and say it actually looks like the original but flipped. Right? Is everybody kind of seeing that? Like I took this original and I just kind of flipped her over, which means that my inverse and my original are symmetric to each other across some diagonal line. That diagonal line is the line y equals x. So any relation and its inverse are symmetric across the line y equals x. That is just a nice little piece of information that we should have somewhere about functions or relations and their inverse. I don't really think that it warrants a whole lot of graphing practice to see this relationship, so we just are doing one example here, okay? Just know that that is a fact concerning inverses. Does everybody kind of see the symmetry? If we had drawn it perfectly, of course, you would see it a little bit better, but we can kind of see how I just took the shape and I just flipped it across that line, or took it at that line and rotated it. Are we okay? So we've kind of been talking about relations. So relation is really any relationship between x's and y's. We're going to take it one step further and talk about functions and function inverses. So we've talked a little bit very loosely about what functions are. So we're just going to kind of clarify it here. Before we clarify what a function is, I would like to show you the notation we are going to use for inverses. So for a function f of x, its inverse is written as f negative 1 of x. So this does not mean I'm taking my function to the negative 1 power. This is just the notation that mathematicians decided to use for inverses. Okay, so whenever you see an h negative 1 or an f negative 1 or a g negative 1, that means that function is an inverse of the original. For a function to have an inverse, because not every single one does, that function must be what we call one-to-one. A one-to-one function is exactly how it sounds. This means that every x maps to exactly one y, and every y is hit or touched by only one x. In other words, there's no x repetition and there's no y repetition in my set of points for the function. So every x goes to exactly one y, and every y is mapped to by only one x. So I can't, for example, take the square root of 4, because the square root of 4 is both 2 and negative 2. So both of those numbers map to the same y, which makes it not a function. So if I take the square root of 4, that is both positive and negative 2. So it goes to more than one number, and more than one number go to it. Because if I square 2, it goes to 4. And if I square negative 2, it goes to 4. So I had two x's that mapped to it. So that is an impossibility. That is not a one-to-one function. Does that kind of make sense? I'm going to show you a trick for deciding whether a function in a graph is one-to-one or not. That doesn't require you to think about it algebraically at all, which is awesome. And this test, because that's exactly what it is called the horizontal line test.
Sounds something I could fail.
So to determine whether a graph is one-to-one, we use the horizontal line test. This horizontal line test, exactly as it sounds, says that if I have some function, we'll say I have this one right here. If I were to draw a horizontal line anywhere through that graph, and my horizontal line touches that graph in more than one place, it is not one-to-one. If it only touches in one place, then it's okay. But if even one of my horizontal lines fails, that function is not one-to-one. So as I'm drawing horizontal lines on this graph, am I hitting this graph in more than one place? Yes or no?
Yes.
Yes, I had several of these lines fail. This one hit in 2 spots. This one hit in 2 spots. So did this one. So because one of my lines failed, I know that this entire function failed my horizontal line test. So this is not one-to-one, which means I cannot find the inverse to that function. One exists, but it's not a true inverse. We'll go ahead and practice this again. Let's say I have, I don't know. That super nice, pretty function. Let's test that to see if it is one-to-one and if it has an inverse. So I draw a horizontal line. Did it pass through more than one time? No. Am I done testing then?
No.
No, I got to keep going to prove that all of my lines will pass. So I draw another one. How many times did it pass through? 1. So far, so good. I draw another one, I don't know, right here. How many times did that pass through my graph? 1, so it passed, so I'm done, correct? No, I keep testing until I prove without a doubt that no singular line will pass through more than one time. Do I know whether this function is one-to-one already? Can you tell? Yes. How do you know this?
Because the line will.
Because I can see a point where if I were to draw a horizontal line, it would pass through more than one time. So this one also is not one-to-one, and thus we cannot take the inverse of it. Does that kind of make sense?
Yeah.
Okay, we're going to do one more, just because I think it's a really fun thing to practice. So let's say I have that one. Just by looking at it, do you think this one will pass the horizontal line test or fail the horizontal line test? Pass. Okay, it's pretty easy to look at it. I can kind of already see that no matter where I draw a horizontal line, it's going to pass. I should still show it though by drawing a couple horizontal lines just to verify that what I see is in fact true. Awesome, it passed. So this is a one-to-one function. So it has an inverse. If it is not one-to-one, there is no inverse to find. Are we all okay with that? Okay. So now that we have shown how to decide whether a function has an inverse or not, now let's actually find the inverse. So given a graph like this, we couldn't actually find the inverse, short of writing out every single one of the points that exist on this graph, which would take me years. So I'm not going to do it. We really only find inverses if we're giving an algebraic function. So let's say, for example, I wanted to find the inverse of the function y equals x plus 5. Out of curiosity, what do you think we're going to have to do in order to find the inverse for this function? Different question. When we looked at that original relation from the beginning of our notes, and we looked at the inverse, what happened to my x's and my y's? They flipped spots. So that same thing is going to happen here. Wherever my y is, that's going to become an x. Wherever my x or x's are, those are going to become y's. So to find my inverse, the first thing I need to do is swap my x and my y. Now it is as simple as solving for y and getting y by itself. That's all I have to do. So what am I going to do to get y by itself here? Subtract the 5 to the other side. And I get x minus 5 equals y. Which means, formally written, my inverse, so y to the negative 1, is equal to x minus 5. That is exactly how I want your inverse written every single time. Okay, I want it with that negative 1 notation. And then that's it. I will move up. I'm sorry, Christina. Does that kind of make sense to everybody who can see it? So we just switched our x's and our y's, and we solved for y. Sometimes they're a little bit harder because we could have more than one y present, or the functions themselves could be a little bit more complex. But the idea is still the same. I want y by itself, and then my inverse is complete. Let's do another one.
Are we gonna expand on this any day or no?
Yes, we're gonna do a little bit more. Oh, this is honestly pretty close to it. Not gonna lie. Okay. So let's go ahead and do another one. So let's say, for example, that I have the function f of x equals x squared plus 1. I have an issue with this function.
No.
I don't have a y.
We can just put one.
But doesn't f of x equal y?
Oh, wait, say it again. Who said it?
Doesn't f of x equal y?
This is just a different notation for y equals. So I can replace that f of x with the y that I know it's equivalent to. And I can rewrite it as y equals x squared plus 1. And now I can do exactly what I have to find my inverse, which is?
Do the XY thing.
Switch the x and the y. Yes, that is what we do. So I now have x equals y squared plus 1. My goal is to get y by itself. So what do? Subtract the 1 over, and I get x minus 1 equals y squared. I have to get rid of the square. What do? Square root it. This is where this is a little bit different. Okay? Because technically when I square root this, I'm going to get 2 answers for that x minus 1 when I square root it, right? Because when we square root in an equation, I get a positive answer and a negative answer. Because that technically does not work with functions, we assume we're only getting the positive version. So I only want the positive version of a square root. And then a square root, okay? So whenever we are doing an inverse and you must square root, only take the positive version. So that means that I end up with y equals positive square root of x minus 1. Is that how I leave my answer?
No, you need the 1.
I need the y negative 1, which is the inverse notation. Technically, if we want to get super duper fancy here, I wasn't originally given this function as y equals, was I?
Or you could put that.
I originally had f of x, which means my actual inverse notation should be f negative 1 of x equals the square root of x minus 1. I would accept either of these as your answer though.
We don't have to put a like a positive sign or anything?
No, because we automatically assume it's positive. There's no negative
Oh,
up front.
okay.
You can put a plus though, and I would not count that wrong. Questions, concerns, or issues so far? Is that pretty straightforward? Flip the x and the y, solve for y, you're good to go. No major issues with that? Okay, so now we're gonna go ahead and move on to the last little part that goes with function inverses.
We'll have to write them right.
No essay here. No, well, you have to write a little bit, but nothing crazy. So instead of being given one function, we could also be presented with the problem where we have two functions and we have to determine whether they are inverses of each other. So the rule that goes along with this is that you can determine if two functions are inverses of each other based off of their compositions. So specifically, if I have two functions, f of x and g of x, if the composition f of g of x simplifies to just being x, then they are inverses. But I also have to check the opposite direction. So f of g of x must equal x, and g of f of x must equal x. So the composition both directions must simplify out to being only x. If it doesn't, they are not inverses of each other. Of course, we're going to do some examples because I know that's kind of confusing. But then this is the last little piece for the homework and for today's lesson. Miranda, are you okay? Thank goodness it's the weekend tomorrow, right? Are we all done writing?
For now.
No. No. We got out here at 45, right? 50, 45. I don't remember.
Here, I got you.
Oh, I have it right here. I don't know why. Yeah, 45. We still have 20 minutes.
Oh my god.
We are flying.
I feel like that.
Okay,
I
now.
feel like it's taking forever. No, you're gonna have homework time. That's
No,
awesome.
that means we can take a nap.
Right now, after the lesson, if you wanted to nap. Speed it up. Is it one? Yes. Okay, let's do some examples.
Let's do it.
Shane wants his nap.
I need it.
My computer.
Okay, so what we're doing is determining whether the following functions are inverses to each other. So for my first example, I have the function f of x equals 3x plus 9, and g of x equals 1/3 x minus 3. And I want to use compositions to determine whether these are inverses of each other. So I'm going to have to test the composition both ways. So f of g and g of f. I always like to do f of g first. So we're going to find f of g of x, which, due to yesterday's lesson, we know is the same as f. with g plugged into it. So I take my 3x plus 9. Where the x is, I replace it with my entire g function, which is 1/3 x minus 3. So this becomes 3 times 1/3 x minus 3, and then plus 9. I will distribute the 3 out. When I do, I get 3 times 1/3 is what? What's 3 times 1/3? Just 1.
1x.
So 1x just becomes x. 3 times a negative 3, negative 9, and then I have a plus 9 at the end. I simplify that farther, and what do I notice?
1x.
The negative 9 and the plus 9 cancel, and I'm just left with an x.
Okay.
So far, they look like inverses.
I have a question.
Yes,
What if it's a negative 1?
not the same.
Okay.
Has to be exactly x. Yep. So I tested one direction. Now I have to test the other direction. So now I'm going to do g of f of x. So that is the same as having g with f plugged into it, which means I'm going to have 1/3 times 3x plus 9, and then minus 3.
Or we can divide.
So I'll divide each of the things inside by 3, yes. So I distribute the 1/3, which is the same as dividing by 3, into the 3x and the 9. 3 divided by 3 is 1, plus 9 divided by 3 is 3, and then I have the minus 3 at the end. So I have x plus 3 minus 3, which will simplify to what? So because both of my compositions came out to be x, what do I know about f and g? They are inverses.
One of them, we figure out one of them,
If one of them fails, we stop.
we stop.
Yep, they are not inverses if one of them fails.
Is there gonna be, like, there's gonna be one of them, but then,
Never know. Okay, so we did one example where they both worked. So now we're going to do one example where one of them is going to fail. Okay?
But I know what it's gonna be inverse or not.
Huh?
I'm putting my money on they're not inverse.
You're putting your, so I should do one where they are inverses?
You just stick to what you said.
Any questions on this composition? I don't feel the need to do all of the examples in the notes because we just did composition. So I feel like you guys already know how to do it. We don't need to practice it a bunch. Am I wrong or am I right? Do we want to do lots of composition examples?
No.
I didn't think so. So let's do one more and then we will be done with today's notes.
I need to start a whole new sheet of paper.
I'm sorry.
I know, I'm trying to fit it all in one spot.
I want to.
This is a waste of
It's
Oh
very
my,
clear.
oh my god.
Math is
I'm
never a
trying to
waste
keep
of
it all in one page.
I'm gonna try to fill out this whole paper with just one bar.
Okay, so my next set of functions that I'm testing to see if they are in fact inverses of each other
Oh, no.
are the function f of x equals 4x squared and g of x equals 2 times the square root of x. It does not matter which composition we choose to do first. I, again, like to do f of g first, but that's just me. It doesn't matter which one you guys choose to do first, okay? Yes,
If it was the square root of 2x, would they be inverses?
if it was the square root of 2x, maybe. Oh,
Just fine.
I don't know how to do that.
maybe you have to.
I'll be honest, I have no idea.
I'll show you. That's perfect.
So if we happen to guess which one fails first, does that mean we can just stop after the one that fails?
Yeah, once you get one that fails, you're done. They can't possibly be inverses. So let's do f of g, because that's the one that I want to do.
That's the
Is
one
that
that
the one that
works.
So let's go ahead and do f of g of x, which means I'm taking g and I'm plugging it in to f. Right, we're okay with that?
Yeah.
So I'm going to take that 4x squared, and where the x is, I'm going to replace it with 2 root x. So this becomes 4 times 2 root x squared.
Wait, you only do the square first.
We'll do the square first, yeah. So since I'm taking 2 root x and I'm squaring it, that means I square the 2 and I square the square root. So that's going to turn into 4x. So then this becomes 4 times 4x, which equals what? What's 4 times 4x? Is that equal to x?
No.
So not inverses. I can stop right there.
All right, goodbye.
Once you get one composition that fails, you are done. Questions, concerns, or issues there? I would like a 1 to 5 from everybody. How do we feel about function inverses? So that includes finding an inverse, using the horizontal line test to determine 1 to 1, and then checking to see if 2 functions are inverses of each other. Anna, what you thinking? 1 to 5. 1, absolutely no idea. Oh, you had to pick up. Sorry, I couldn't tell you.
My back.
Okay, so homework is on Canvas. I suggest that you go ahead and look at the homework and at least try some of the problems before you take a nap.
Yeah.
I was gonna dream about doing
Oh,
that, so I'm seeing